All right, so welcome everyone. Thanks for the introduction. Today's session is on enterprise cloud patterns for Java developers. So we'll see a little bit of Java code, but not that much, to be honest with you. But we can dive into some of the topics and around the code and all that kind of stuff. But this is more of a high-level architecture presentation rather than a code-heavy one. The other ones I do tend to be more code-heavy. So already did a bit of introduction. Based out of Atlanta, I help with Atlanta Java user group. So it's always great to speak at another Java user group. And the most important thing on this slide is my Twitter handles. If you have any questions or follow-up, you can hit me on DM on Twitter, and we can continue the conversation. So a couple of quick words from the company that I work for. I work for a company called Azul. And in my opinion, we make the best JVM in the galaxy. So we also make open source JVMs as well as a proprietary high performance JDK called Azul Platform Prime. And the reason why it's so great is because it has huge performance improvements for especially long running Java tasks. So a lot of our customers use it for low latency types of environments like trading. And also they use it for high demand environments like running a Kafka cluster, for example, or Spark cluster, or Cassandra, and all those types of things. So if you do any type of big data stuff that is based on Java, you can use Azul Platform Prime and get huge savings. And of course, all of you are familiar, almost all JDKs are interchangeable. The open source builds of Azul and the Azul Platform Prime, no code changes. You just drop it in and off you go. You get more stability, better throughput, and of course, cloud savings with that higher throughput and performance. So you get faster performance and cost savings. And last time I checked, AWS was not cheap. So very expensive. Oh, and one more thing. I posted this in the Meetup group page. If you want to get one of these fancy Keep Calm and Use JDK 17 t-shirts, you can go to this URL. But I posted it onto the Meetup in the comments, so you can just click on the link. And we'll ship you a free JDK 17 t-shirt so that the people that you live with can be not impressed that you're wearing a JDK 17 t-shirt. But who knows? One final thing. One of the things that we're part of is a community-led effort called Foojay, which is Friends of OpenJDK, but it's a place where lots of people write articles on Java and Cloud and other things like that. And you can also contribute. So it's totally free to create an account, and you can go and blog or whatever if you don't already have your own place to do that kind of stuff. Okay. All right, so let's get started. We'll talk for a few minutes, but not too long, about the overall philosophy behind enterprise cloud patterns. And then we'll do a quick review of cloud native and what that means. I don't want to spend too much time on that because I'd rather jump into the core of the presentation, which is talking about the patterns and what that means. Very quickly, for those of you who are already on the cloud and maybe looking to move to the cloud, what are some of the kind of differences between running a monolith versus running in the cloud, right? A lot of people know this, but I like to do a review just to set like a foundation for where these enterprise cloud patterns build from. So when we think of a monolith is not elastic. It's basically, I'm going to provision a server or a set of servers, and if you want to expand it, you have to fill out a TPS report triplicate and send it around. It takes a lot of time to do that. Whereas the primary philosophy behind the cloud is that it's elastic. That means you can provision more compute power, more storage, more whatever you need on demand and very quickly. It doesn't take any time to do that. And the key tenet out of this is that when we're building applications for the cloud, whether they're Java apps, or Node apps or Python or whatever, we have to design for elasticity up front. Now, this is a little bit difficult to say because if you're a software engineer, you know the root of all evil is too much upfront design, otherwise known as pre-optimization, right, or over-engineering. So, but when you're building for the cloud, you do have to think about that elasticity upfront. Otherwise, you can spend a lot of time later or run into problems later when you don't take that into account. Now, the other key difference is that we have to do horizontal scaling when we go to the cloud, because we can typically only add but so much compute power in a single quote-unquote server, right? So we think in terms of cloud, and we think in terms of horizontal scaling. But that also means that your entire architecture has to be scalable too. It has to be elastic. So if any part of your overall architecture is not elastic, then you've created a bottleneck, right? And something that may be very difficult to actually figure out how to fix if you don't think of it up front. All right, so when we think of elastic, I mentioned this already, compute, network, storage, et cetera, all those things need to be elastic, and you need to think about those things up front a little bit, not too much, right? And if we take a step back and think, but why do we need to be elastic and horizontal scaling and stuff like that? Well, the first reason is cost. When we think of the cloud and we think of elastic, we can do on-demand compute. And I know for big data projects that I've done in the past, I've literally spun up a server with 30 gigs of RAM, 32 gigs of RAM, loaded data onto it, run computation on it for like a couple of hours, and then spin it down so I don't have to keep paying for it, right? So there's the whole cost angle around this. And of course, with that comes the ability to have that adaptability and agility for being able to scale up and scale down as you need. And of course, when you keep elastic in mind up front, you can also get faster time to market because you have to wait for servers to be provisioned. And if you use a CI and CD pipeline that allow you to deploy very quickly, again, you can push changes faster and more frequently into a cloud and elastic type of environment. All right, so I'm going to breeze through this really quickly because I want to get to the core of the presentation, which is around the enterprise cloud patterns themselves. But microservices and cloud native, everybody knows about Docker and containerization nowadays. Dynamic orchestration. This one is a little bit of, well, do we really need to do a lot of dynamic orchestration? Is it kind of a thing that we have to focus on a lot? I'm not so sure about that after working in the field with people at both this job and a previous job. Do we need to have that auto-scaling Kubernetes? Is that really necessary? Or can we think about right-sizing our kube cluster up front rather than spending a lot of time trying to get all the kinks worked out of auto-scaling a kube cluster, for example, right? Of course, cloud native also means microservices oriented, right? So I'm not going to talk about all these things. Most people know that containerization means that you package stuff into a container so that you get reproducibility, transparency, and resource isolation. Containers are for dynamic orchestration, what we were talking about a second ago with Kubernetes scaling up and down. Right, dynamic resource utilization. Applications are not this big, but they're this big now, i.e. smaller chunks or microservices so that they're more easy to do bug fixes on and patches and get more agility around that. But this will become a bit more important when we talk about some of the patterns in a second, right? When you build a monolith like that's this big, all of your connections between your code and modules are at a low code level. But when you build microservices, your dependencies are between microservices and other services that you may be using off the shelf. We'll talk about that in a few minutes. Okay. Microservices, obviously, something that's small is easier to understand and build for than something that's large. Right? Horizontal scaling. The key point on this slide is that we have to design more for stateless applications now rather than stateful applications because of the nature of what we're building. You can have stateful microservices, but that means you need to have some way to synchronize state between microservices. Sometimes that means putting it into a database or an in-memory data layer like Redis, right? But then you're adding complexity when you do that. We'll talk about that also in a few minutes. So microservices is a distributed systems model rather than a distributed code model, right? We want to try to avoid dependencies. We'll get into that in a few minutes. It's harder to manage and monitor a microservices-based application because now you have your app in multiple places. And that's pretty much the quick review, right? We'll dig into some of these topics as we talk about some of these patterns, but there are a lot of these enterprise cloud patterns. We're only going to cover a few of them today. And when we think about Java, where does that fit into the picture, right? So this is one of those things where when people build apps today and they think of microservices, they think, well, we need to build them in Go, or we need to build them in JavaScript or something like that. But in my opinion, Java is still very much a very good environment for building microservices because nowadays Java starts up fast. You can build small Java applications using modern frameworks like Quarkus and Micronaut. You don't have to use a massive Spring Boot app to build an application anymore. You have alternatives to do that, right? And as we work through these patterns, you'll probably recognize some similarities to low-level patterns that you've seen before. So, for example, we'll talk about the observer pattern and the adapter pattern, or you know about those patterns. We'll see them not at a code level, but at a higher systems level as we go through this. All right, so we're not going to cover all of the patterns, but I do want to show you what some of the categories of these different patterns are. They're roughly broken down into 4 different categories: design and implementation, performance and scalability, data management, and availability and resiliency. So tonight, we're only going to talk about the first one. I'm working on the third one, or the presentation for the third one, data management, and then eventually I'm going to do all 4 of these and have a full catalog of these. But tonight, just design and implementation. And out of those patterns, we'll only cover maybe 5 or 6, which I think are useful for Java developers, especially those coming from a monolith type of environment, right? And moving or migrating to the cloud. All right, so the first one we want to talk about is what's known as the ambassador pattern. All right, so let's talk about this. The ambassador pattern is specifically useful for doing legacy app transitioning. Right, so if you have a legacy app, whether it's a big monolith or a smaller application, and you need isolation and other things like that, that's what the ambassador is for. And if we look at it visually, you have a client or service, and it calls into this ambassador pattern, which is essentially at its core just a proxy that puts cloud native features onto a legacy application where it may be too difficult to put some of those features onto. So some of those features are monitoring, retry, maybe a protocol adapter of some kind, right? So that is the core of the ambassador pattern. Not very complicated, but the idea is that it gives you the things that you would normally expect from an application that you built to be cloud native upfront, but you essentially wrap it around an ambassador pattern style of service. And the protocol adapter is the interesting part of this, I think, because everyone understands monitoring and retry, right? The protocol adapter is basically if you have something like a legacy application using SOAP, for example, and it's like, well, we're not going to put that into our modern cloud native style architecture. So what you can do is inside your ambassador pattern, you make a SOAP call down to your legacy app, and on the front end, maybe you just use standard REST and JSON, right? Or whatever. Okay, so the protocol adapter, actually, there are other things you could use this for. If you also have some kind of terminal scraping, TN, 3270 or something, you can use this to wrap those old legacy services so that they still have cloud native features like monitoring and retry, but you don't want to go and refactor that code because it's written in COBOL and it's like 30 years old or something. So, and this specific pattern is more for end clients, right? So we'll talk about a variation of this, which is meant for more service-to-service type of things in just a second. Okay. So relatively simple. It's a proxy, allows for resiliency and other cloud-native features, as I mentioned. And one thing to note is that typically the proxy is a separate process, and you can often implement this as a sidecar in Kubernetes. Okay, so there are a number of different ways you can do this. You can do this in Java, of course, or you could just use a Go-based proxy that you can sidecar into your Kubernetes node. And we talked about some of the features already. And when we think of what are some of the specific ways we could implement this in Java, if you're using Spring, you could use, for example, the health check feature and the Spring REST template, now called the web client in the latest version of Spring, to actually build out this pattern for yourself. And if you're using MicroProfile, they also have a RESTful client that allows you to quickly build this type of pattern for yourself. All right, so if we look at some code here, let's see if this works. Okay, yep. So what we're doing, and this is a Spring-based example, you can see we say public response entity, and we create a request body. And again, this is Spring-specific code. But the interesting part is right here. You could see that we go and call some other service. In this case, it's just an HTTP service. So this is where your protocol adapter could go, and you could talk SOAP down to something or whatever, right? Does anyone still use RMI or Corba? I don't think so. But if you do, you could write your RMI or Corba code here to call into that. And the rest of this is just boilerplate for making that call and returning a response. Okay. All right. So the next pattern that we want to talk about is the anti-corruption pattern. And again, this is also useful for legacy app transitioning. So what does this look like? Right. So you have your cloud native application. Right. So you have a microservice. You have a cloud function. Maybe you're doing stuff using Kafka in an event-driven application type of environment. And again, you have your legacy app here. And what we want to do with this anti-corruption pattern, as the name implies, is we want to have some protection for our legacy application so that it doesn't get overwhelmed or that we don't send bad data to it or whatever, those types of things. Right. So this is, again, it's a proxy type, almost a proxy type of solution here. But the key difference from the ambassador is that the ambassador patterns is meant more for end clients, and this is meant more for service to service calls. So this is where you would go and do things like flow control, right? Because your legacy app may be able to only handle 100 requests a second or something like that. So your anti-corruption pattern would provide some kind of internal queuing so that you don't overwhelm your legacy app, and then then you have to send somebody in a data center to go and reboot a mainframe or something like that. I don't know, right? Of course, I'm being a little sarcastic when I say mainframe. This could be any legacy application, including your 10-year-old Spring Boot application, for example. Okay, so again, it's a little bit more sophisticated than an ambassador. It's not just a straight proxy. The idea is that you're able to construct something that has more logic around protection and flow control and other things like that. And as you guessed it, the previous one and this pattern are both examples of a standard facade or adapter pattern, right? It's meant to firewall legacy applications, and it's useful to migrate large legacy apps to the cloud, right? Especially in this case, we're talking about service to service type of things. It can also have protocol adapters. And one thing I think I'd like to point out here is that oftentimes you have something that is a legacy API where the folks who wrote it left a long time ago and nobody knows what that code does. And you don't necessarily want to disturb it while you're going off and refactoring it over here into a more modern style. And you want to do compartmentalization of it. This is kind of the idea behind this. Okay. All right, so some Java specific notes. Again, if you're building this specific pattern in Java code, you can use a Spring REST template or microprofile REST client. But again, you have to explicitly code entry points and proxy them to your legacy application. Okay, all right, swiftly on. Let's talk about the gateway aggregation pattern. This one is a little bit more exciting, if that's the right word, right? Now, your app still needs to call multiple services. When we think especially about a microservice style architecture, right? And we think about what do we need to do now? Because before what we were doing is we were writing Java code and we had, for lack of a better way of saying it, modules within our Java application. It could just be a package or a class, but let's think of it as a module. One module needs to call another module, that may call another module, and there may be interdependencies between them. But how did we deal with that in Java code? We basically just said, okay, go call that thing, because we were operating down at the code level inside of a monolith, inside of the same JVM. So you literally would just look up the class. If you're using Spring, you do dependency injection, say, okay, go and call this to go and authenticate the user. Go and call this thing to get data about the user out of the database, et cetera, right? So apps still need to call other services. Now, what this specific pattern does is it aggregates multiple services. For example, service A, B, and C need to be called either by a client or by some other service. And when it's invoked, we want to return the aggregation of those three services being called. Now, if you're me, when you first looked at this, you're like, why do we need this complexity? Right? Why doesn't this client or service just directly call here into A, into B, and into C, right? And the short answer is that you have to start considering this once you get a larger number of microservices, or let's just call them services, calling each other. Because what can happen is that you eventually end up with what's known as the Death Star pattern. Okay? It helps to avoid this Death Star pattern. So what you can do is you can group together different services so that you don't have as many interdependencies between services. So that's what we want to try to avoid, because otherwise you end up with something like this. Some of you may have seen this picture before, right? So this is Amazon.com and Netflix here. I think the Netflix example is probably a little bit easier to understand, right? Netflix was one of the first companies to go microservices. And what happened, I mean, Netflix is a big company, right? You can just imagine the many thousands of microservices they have for internal and for external facing types of features for their platform, right? Movie reviews, movie recommendations, user login, user profile, blah, 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 right? Thousands and thousands of these services. And this is actually taken from an article that was written by Netflix. It's actually an old article now, maybe like 5 or 6 or maybe even 7 years ago, because they were on the leading edge of this whole cloud native and microservice thing, right? But if your architecture ends up looking like this, where you have all these services calling each other, you essentially end up with an entangled mess of things. And oftentimes, the gateway aggregation pattern is a good way to encapsulate and enclose a group of microservices so that you reduce the number of interdependencies between them. Okay. All right, so it aggregates calls to services. The client interacts with the gateway rather than directly with services. Right? So one of the problems with introducing this thing, of course, is that what happens if you have an error in that sequence of services that you're aggregating together? You have to think about now, okay, now that I'm doing this, how do I appropriately handle errors that may happen or failures that may happen downstream? So as you guys know, there is nothing free in software programming. Everything in software architecture especially is just a series of trade-offs. So this is one of the trade-offs you're making. You're adding a little bit of complexity on this side to reduce overall complexity on the other side. Okay. So you can write this, again, using an async REST template. And we can talk about GraphQL a little bit also. Now, when I think about GraphQL, actually, I think of GraphQL in some ways as a gateway aggregator. Because when you're building a GraphQL endpoint, what you're typically doing is you're taking stuff from here and taking stuff from here, and you're lumping it all. Lump is not the right word. You're assembling it all together into a single endpoint that you're calling. And you can keep adding onto that GraphQL endpoint to get multiple things, right? The whole point behind GraphQL is that instead of saying, make a RESTful call to get the user, make a RESTful call to get the user's profile, make a RESTful call to get all the items in the user's cart, make a RESTful call to go and get their recommended shopping items or whatever, right? You made 5 calls there. Point behind GraphQL is that I can make one call and get all 5 of those things all at once instead of making 5 unique calls and having to wait for each one to complete before showing what the user needs. So in a lot of ways, GraphQL is a great gateway aggregator, but again, you get that coupling with it and you have to handle downstream failures. And if you're familiar with GraphQL, one of the things that you can do with GraphQL is you don't necessarily have to make a direct database call in your GraphQL instance. A GraphQL program, basically a GraphQL endpoint, can call other endpoints and aggregate that way as well, right? So GraphQL is not necessarily limited to making just low-level code calls. You can access the network, you can access the database, you can access other APIs, et cetera, et cetera. Okay, so just want to throw that in. We'll talk a little bit more about GraphQL in a second. Okay, now, here's an example in Spring of building out a gateway aggregator. Right? What I'm using here is, this is a standard at-get mapping right here. You can see I have an async REST template, and then I'm using 3 computable futures, completable futures, to go and call 3 different URLs And then if you're familiar with completable features, anyone used a completable feature before? Okay, a couple folks? Okay, cool. So you're familiar with how this works. Completable feature, go and run all these things, get all the results, blah, 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 and then set the entity back, right? So it's relatively straightforward. And unfortunately, for almost all of these things, there's not a higher level library for implementing these patterns, but I think it would make a great open source project if anybody has some free time. So. All right, let's move on to the next one. This one is BFF, or Backend for Frontend. The point of the BFF, or the Backend for Frontend, is to get flexibility and performance for your clients. Okay, we'll talk a little bit about kind of organizational things around that in a second. But let's look at my very badly drawn diagram here. We have three different types of clients: native mobile app, a web application, or web mobile application, and a desktop web application that all need to go and get either to a legacy app or a microservice or whatever. Now, what we do for backend for front end is we say, let's create a backend for front end app for each one of our front ends. So what we're doing here is we're trying to optimize for each one of those front ends or things that are calling into our backend. Right? So these services at the bottom are just returning the same data, but it's these things in the middle, our BFFs, that take that and maybe take only the data they need or shape the data in a specific way. So for example, for desktop web, we may return like a very big JSON because we know it'll probably be on Wi-Fi and it'll be fast. We may also include references to images in our data, which are like bigger images. Whereas if someone is coming from the mobile web, maybe we'll include less data or less rows of data. Maybe we'll include URLs to images, which are optimized for a phone, et cetera, et cetera. Of course, for native mobile, depending on which platform you're on, Android or iOS, you may want to ship a whole different style of data to them or a format of data to them, right? Optimized for that specific platform. And the reason why I said that this is kind of an organizational thing too, is that this is a good way to keep your front end teams happy. Because instead of them having to adapt to what's down here at the bottom layer, you can provide them with a more friendly layer for them to go and get their data and get in the format that they expect and with, you know, structure and other things like that, right? All right, so one interesting thing about this is this can be an implementation of the previous pattern we talked about, which is a gateway aggregation pattern. Okay. All right, so this also begs the question, we talked about this a few minutes ago. Where's the line between doing optimization and premature optimization? So sometimes you have to be careful. Maybe you don't need to do this. Maybe it is a good idea to do this. Are you doing premature optimization? That depends on the use case, of course, right, or where you're at. Right. Again, the general premise is we create a separate backend service for each front end, and data can be shaped and sized for specific needs. The whole point of this is we get improved performance. We may get some code duplication, and we already talked about the structure of our team or how we work with our front-end team and our back-end team and stuff like that. We also spoke a little bit about this, right? What about REST versus GraphQL in this case? So I don't want to rehash what I talked about in terms of GraphQL, but this may also be a place where we take a back-end service which is implemented as REST, and we expose that and some other services, we bundle it together in a GraphQL endpoint because it might make sense for a desktop web client or mobile web client, right? Or even a native mobile client. So this is a good place to think about that. If you're doing a backend for front end, then maybe we can think about using GraphQL because that might be the right thing to do in this case, right? We're already introducing that layer to go and do the right sizing of our data and stuff like that. So maybe it's a good place to think about that. And if you're building this from scratch, there's the async REST template. We already looked at a completable future example. And then, of course, if you're in the Spring universe, there are a couple of things that you can use for doing GraphQL. There is a standard Java-based GraphQL library, which is very difficult to use and very low level. But there is another one which is a little bit higher level where you can use annotations to build a GraphQL API in Spring, right? I don't remember the name of that off the top of my head though, but there is one available to do that. What's that?
It's the Spring GraphQL.
Yeah, I don't think it's called that. Actually, I don't think it's from the Spring people. So what I find interesting is that, and I could be wrong because I haven't looked in a while. What I find interesting is the Spring people haven't come up with a really nice GraphQL library that, you know, is Spring GraphQL. It's some third-party folks that have done it. I would have thought they would have done it by now. Maybe they have. I haven't looked in probably a year or something. So. All right, let's move on to the next one, which is the gateway routing pattern, right? And this is already used. I think almost everybody who does something in the cloud already uses this. And sometimes I say it's already commonly misused as being tongue-in-cheek. But this is essentially what we know already as API gateways, right? API gateways were all the rage 5 years ago. And everyone was like, we have to use an API gateway for everything. And API gateways are a kind of gateway router. But let's see what this looks like in a roughly drawn diagram, right? So we have our service, wrong button. Yeah, we have our service, or we have a client, and then we have some kind of gateway router. Inside this gateway router, we configure /user, /profile, /cart, whatever, right? Everyone's familiar with this. And then this thing goes and takes those calls. If it's for a user, it goes through here and calls some underlying user service. If it's for a profile, it goes and calls this other service, et cetera, right? So we use this to basically have a single entry point for our underlying services that would be living at multiple different endpoints. Let's say URLs. Maybe URLs isn't the best way to put it. How about servers, right? So you could have something like api.azul.com, and that's where all the traffic would go because that's what our gateway router was called. And then underneath it could be like, you know, server1 dot blah, 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 and it would just route it through that, right? So the common usage was, well, let's just have one entry point into everything. And these API and these gateway routers or API gateways have been very common on all of the cloud service providers for years. Of course, they're not free. You have to pay for every call that goes through them. It's a very small amount, but you know, if you have millions of calls, it can add up. So, okay. So gateway routing, used as a gateway for downstream services, gateway routes to the appropriate service. And you can typically, if you're using an off-the-shelf one, you can typically do some kind of abstraction in there too. One thing that's common in API gateways, as all of you know today, is that you can do authentication that's directly built into the API gateway so that you don't have to do it. It'll just use your cloud providers or whatever authentication mechanism and authorization mechanism you just plug in that's provided by your cloud provider or whatever platform you're using. Okay, and part of the rationale, aside from having a single place that you just put into your clients, is that it helps to minimize changes to the clients because you don't have to change the location inside of the client itself. You can just go into the API gateway or API router and say, oh, this service now lives over here, and you don't have to change the client anymore, right? Because you're abstracting that over there. And one thing that you get with this is it does reduce the coupling directly to services, which can be very, very nice. You can probably think of lots of use cases. One I just talked about, if you move the service from server 1 to server 2, who cares? Just go update the API gateway, and your clients don't know any different that it's changed. All right, but yes, API gateway and gateway routers are just another facade-based pattern. So I like to say in software engineering, everything that's old always comes back to life sooner or later, and that's where we're at now. Instead of having complexity and applying these patterns down here at the code level, we apply them up here at the module or systems level now, right? Yep.
Does it work with Kubernetes?
So Kubernetes in some ways, I'm going to try to remember, maybe some folks in the audience can correct me. There's already some Kubernetes infrastructure which has an API gateway or router built into it, isn't there?
Yes, it's here.
Right, but that's like
gateway, which
right.
is very similar to
Right, but it's not as quite as sophisticated as this. But you basically, my point is, you can go and configure that directly in your Kubernetes environment. Right, you can always front end it. Yeah, that's right. But typically, like that's what I call low level API routing, right? That's basically just for within the kube cluster itself, right? So it's like, let's say it's like down here. When I think of an API gateway or gateway routing, I think of it as a peer. So it routes from this user kube cluster to, and then you have a profile kube cluster, and you have, I don't know, a shopping cart kube cluster. So the routing is up here, less so down here. Right, that's the basic idea, right? Yeah, the Kubernetes routing stuff, that's for just within the kube cluster itself for low-level management. Yeah, go ahead.
We'll just add it the ingress. There is an ingress controller.
Ingress controller, yep.
Most likely, and occasionally they do let you route outside of the cluster. But
oh, you can route outside the cluster?
Occasionally, you can say
okay
to a URL or something.
It will just go get it. Okay.
But yeah, just like Nginx, because a lot of times it's in the controller.
That's right. It's usually just to Nginx or something, right? Yeah. Well, this is another problem with software developers is if you give them the option to do something like that, they'll do it. It may not be the right thing to do, right? Because rather than routing up, you'd rather have that routing happening up here rather than down here. Because if you do it down here, what happens? You've created a dependency from here to somewhere up here, right? So typically you want, when you're thinking architecturally, you want the dependencies to flow in one direction and not in both directions. Because what happens when you flow dependencies in both directions, you create tight coupling. And you want to avoid that type of that coupling. It makes it more difficult to make changes then, right? So I'm sure all of you run into this at the code level, at least, and probably at the systems level by now if you've been building cube stuff or whatever. All right, so a couple more quick points. There's some trade-offs. When you add this, of course, you can get a latency bottleneck, and you may also create a single point of failure. I put a question mark there because typically these gateway routers, or especially if you're using an off-the-shelf API gateway, it's also distributed, right? They have their own thing that distributes internally within the API gateway layer so that if one instance of the router goes down, it'll just route to some other instance that's already alive. Okay, and of course, you can write one yourself using RESTful end controller, but like I said, most people nowadays use an off-the-shelf API router or just use their cloud platform's API gateway. Because why not? It's the easiest thing to do. Just have to write 8,000 lines of YAML and you're all set. All right, and so that's it. Let's see, we'll do a quick time check. Oh, I went through that fairly quickly, 45 minutes. That's about how long it typically takes. So we can take some questions, comments, any other kinds of things you guys want to ask in terms, again, I went through most of that fairly quickly, but yeah, go ahead.
On the ambassador pattern, is this somewhere you also might apply some sort of authentication or any other thing you wanted to add in translation, especially like your legacy system was using like let's say it was just had some built-in user database or something.
Yeah,
migrate to SSL.
Yeah, that's right. Yeah, that's the when I say protocol adapter, I kind of meant both the low-level kind of plumbing as well as the high level, like what does the actual data look like, right? Is it XML or is it like binary or whatever? Yeah, that's the general idea, is that's where you can go and code all those things to make that legacy app more cloud native friendly. I think that's kind of the point I'd like to get across is you want to take this old thing, but you want to use it in this new architecture, but you can't just dump it in this new architecture without providing some kind of like encapsulation, protection, protocol adaptation, data adaptation, and stuff like that. Yeah. Yes, please.
It kind of struck me that these all kind of use that adapter or reverse proxy kind of. Mm-hmm. Would you say that certainly like services or attributes are non-functional? Do they belong in certain places? Like, would you rather put authentication, say, at the gateway than fast or there's certain?
Yeah. So that's a good point. The question is, would we want to have? I think it's called non-functional requirements. Is that the word you're looking for?
Yeah.
non-functional requirements, would they belong here or like at the API gateway level or something? Or
things like
different things, yeah.
ability or that you would put in one place or the other.
Yeah, the short answer is absolutely, right? So I wouldn't do front-end authentication here. But what would go here is, as part of the protocol adapter, if this legacy app needs some kind of authentication, that would be built into here. But the actual end users or the end service auth would be up here. And then you have just the low-level stuff, right? The way I like to think about this and the subsequent one, actually several of these, like this one also, as well as this one, the aggregation and anti-corruption is, I think of it in terms of what do I need to do as a developer to isolate this application from the rest of my architecture so it doesn't poison the rest of it, so it doesn't become a bottleneck. Because I want to build all this nice code in a microservices style and get all the benefits of that. But if I put this thing in here, right, the one bad apple, blah, blah, blah kind of thing. Right. So how do I like put that apple into like a plastic bag or something that like won't corrupt or like cause chaos over here? So that's kind of the mindset I use when I'm thinking about transitioning, like if I'm working with a customer, or if I'm thinking about like, how can I take this old monolith and use it in this kind of newfangled, well, it's not new anymore, but this modern cloud native style. Like, how can I isolate it over here, but still keep using it? Because I can't refactor this right now. I can't rewrite it. Right. So, good.
Put online can post their questions on the chat. I can read out the questions.
Oh, yeah. If people online want to post any questions in the chat, we have a few minutes to still take questions. So. Are you watching the chat?
Yeah.
Oh, he's got the chat open. He's got chat open there.
What I'm just.
Yeah, go ahead. You might as well.
This reminds me a lot of like how service meshes are, but like master things, like pushing out the masters in every single one. Because but even the protocol and that the RBC or something.
Yeah. Yeah, that's right. Service meshes are interesting.
Program that goes into those names.
Yeah. Well, I mean, we could go off on a small rant on service meshes because as an architect, when I think of a service mesh, it's like, whoa, it's like, let's slow down here, because a mesh implies this, right? It implies multiple interdependencies, and that leads me to this very quickly. So when we as an industry started talking about service meshes, I was like, okay, let's hold on. Let's put the brakes on for just a second. It's not what we want to do, because I mentioned earlier, just like in code, why do we do dependency injection? Because that way we don't create dependencies in two directions. When we do dependency injection at the low code level, we do it because what we do is we flow dependencies from the top down through our low level Java code. And in my opinion, when I'm building out an architecture for cloud native, I want to have the same mindset. I want to take something up here. I want to start at the top and flow dependencies downwards, and not have as much as possible things flowing in the other, basically doing a two-way street. Because again, just think of you like, do you guys build with Spring or with, whatever, right? I'm sure everyone has built something with Spring, and you understand the value of DI, right? And why we flow dependencies in one direction. So try to think the same way when I'm building stuff for the cloud. And when I see folks that I work with building applications, and they're like, oh, we'll just call this service over here, and then we'll call this one, and we'll call this one. It's like, hold on, let's think about this for a second, right? It's like, maybe we need to put that into basically an aggregation pattern, because I would rather couple these three services or 5 services, let's say, together, and then have these 100 other services call that one service. Because if I had 100 services calling this aggregated 3 services, let's say 5 services together, if they were allowed to just call each one individually, I've created 500 different connections in my ball of mud here, right? So,
That defeats the purpose of microservices in the first place.
right,
Now, if you get dependencies, how will you update that one service?
exactly. So Ron makes a really good point, right? The reason why we want to reduce the dependencies between services is because if your microservice has too many dependencies, it defeats the purpose of being able to update that microservice frequently, as often as you need, or all those things, right? You basically now take the agility out of that, right, or the ability to change it very quickly out of the picture, because now you have all these dependencies. So it's a good point. Okay, do we have any questions online? No, that's
Well,
okay.
you're reading another problem for the gateway map.
Mm-hmm.
So you can do other things there. Like when people are coming in from the internet, also the web app, can do some security things. Right? So like our data politics, so as so that's one layer. You can isolate all this security stuff. You can do throttling. Right? So if you want to reduce the based on the plan and all that stuff, passing there, we can do analytics. Who's coming from where for the monoliths, things like that, right? So it's kind of a good idea to front end all this stuff.
Yeah, absolutely. Something I wanted to show, if I could pull it up quickly. We have something new coming out next year at Azul, which is this analytics suite. And we would love for you to create super complex, interdependent cloud applications, because then you absolutely need this product then, right? Because what this does is it shows you at a very, very low level what libs you're using in different Java whether they're microservices or whatever, right? And that's the reason why this product was specifically created, was because of that huge number of interdependencies between microservices. Are you using this version of Log4j in production that has a security patch that needs to be applied to it immediately? Because you might include something on the class path. Now, Log4j is not a good example. Let's say you have some internal, right? Jackson's a good one, right? But is in a lot of places they just, okay, let's just include all of our standard libraries in all of our applications. But if you need to do a security patch for that Jackson lib, how do you know exactly which one of your Java applications is actually using it? Or do you shut everything down and bring it back up, right? That's the least efficient thing to do. So anyways, that's something that we're working on, and we're going to have out early next year to show, like at a snapshot, oh, this version of this Jackson library is being used here, here, and here, and is actually being used. So you know exactly what to go and patch and stuff like that. But that's I'll be back next year to talk about that.
It's kind of like the DLL hell.
Yes, DLL hell from the Windows world. Yeah, that's right. Because you don't know sometimes, like, what is actually being used in your Java app, right, in terms of libs. So,
well, but you kind of it kind of also extend into the services at the system level.
well, this is specifically targeted at basically for the JVM. So anywhere you're running Java, you'll be able to get the insights on all the things which are actually happening across all your VMs for all your apps running in the cloud or in your own data center or whatever, right? But nowadays, when I say cloud, I tend to mean, your own data center, cloud, blah, blah, blah. So anyways, this stuff is not quite ready yet. The optimizer suite, connected runtime, which is a new thing that was just announced last week, right, Tom? It's basically a way for you to preload your JVMs with a compiler where the optimization is not happening within the VM itself, but is happening over here. So it can optimize your code ahead of time, and while it's running, it'll optimize it like over here, so that if you're running in a kube cluster in a constrained memory and CPU bound environment, you don't need to increase that. You just need to do it once. It'll push it to all of the different versions of the application running wherever in your company. That was just released last week. But anyway, it's not a product talk. I thought I'd just drop it in because there's some cool stuff happening both at Azul and other places around some of this cloud-based JVM technology. So, yeah. All right. Any questions from the? Okay. So I think we can probably say goodbye to our online audience. So thanks for coming, whoever's watching online. If you have any questions, just drop me a Twitter note here at PR Patel, and look for the second installment of the series, which will be a little bit of a deeper dive into the data patterns for enterprise cloud architecture. I'm hoping to have that done by January. That's what I'll be doing over Christmas. So. Okay, go ahead.
So,
We have two questions from the online audience. Yeah.
Sure. Does the client explicitly needs to specify the type of format? Clients as in web browser or format as in XML or JSON?
Yeah. So I'm not sure exactly the context of the question, but if we're
communicating with the gateway.
Oh, right. So if we're talking about the API gateway, there usually is already a preset specification that's specified by the developer of that service, right? So typically nowadays it's JSON and REST. Okay, so that's the short version of the answer. If you're doing a BFF, you can do whatever you want because you're actually building that backend thing. But typically nowadays, we've settled on doing a RESTful JSON type of endpoint for that type of data, right? But as a developer, you're in full control and you can do what you want.
And then one question from Govind. Are there any patterns for overcoming a retries from on call or in retry or string batch?
Okay. So now we're getting into some nitty gritty. So the question is there any way to avoiding a retry storm when using Spring Batch and what was the other one?
Spring retry.
Spring retry, yeah. Yeah. So this is a little bit of a complex answer, but I'll try to answer it. So what the person's asking is when certain services go down, and they go down for more than a short amount of time, you get what's called a retry storm. That means you have, let's say, 1,000 requests coming in. Your backend service is down for, let's say, 30 seconds. Now you have 30,000 retries which are queued up. Okay, so the best answer to that question is that you have to have some kind of way of detecting across the system how many retries are in the overall queue, not just in the queue for that one, basically that one individual instance of the service. And once it exceeds a specific threshold, basically fail all of them until you can get the system back up to a point where it can start servicing those retries in an appropriate amount of time. So a lot of this is a quote unquote, it depends type of answer. But one common strategy for this is once you've exceeded a specific threshold where you'll never catch up because of the retry storm, you basically have to have a way. And I'm trying to think in Spring, is there a way to go and expire retries? I don't know off the top of my head if there is, but the tricky part there is how do you, if you're running in a cube environment, for example, distributed environment of any kind, this service instance has 1,000, this one has 1,000, blah, blah, blah. So it's all spread out. So it doesn't look like a big problem until you go look at the backend service or the gateway for the backend service, which is just getting pounded. So you have to design a way to keep track of those retries. That's the kind of complex answer. The short answer is you limit the retries to a smaller time window and smaller number of retries until failure, right? So if you set up a retry every 5 seconds and retry 10 times, right? So if you see or if you know that this service is going to go down frequently because it's a legacy service and I don't know, whatever, right? It's not very stable. What you have to do is you say, do 2 or 3 retries, and the retry length window, it can either be moved up or down depending on the use case. Maybe you do a retry after 5 seconds instead of 10, or maybe you do a retry after 30 seconds. But again, there's trade-offs in both of those time intervals. But the kind of easy way to do it is don't do 5 retries, don't do 10 retries, do 3 retries, and that will reduce the overall likelihood of a retry storm. So, okay.
Netflix has a retry mechanism, something. So
yeah.
So thank you.
Yeah, circuit breaker.
Yeah, the circuit breaker, right? Yeah. Well, what I basically described is is there a circuit breaker implementation in Spring? I can't remember if there is. There is, isn't there?
What's the last thing? Is that history?
Yeah.
Hystrix, that's it. That's what I was thinking of. Yeah, Hystrix. Yeah. Yeah, that's right. So yeah. So, you could go and implement a circuit breaker. I think there's a newer implementation.
Resilience for J is called.
Resilience for J. Yeah, there you go. Thank you. Yeah.
Okay, that's on the client. But,
Oh, is that on the client and on the server?
I mean, all the things you're saying, like to reduce the retry or back off, the client, you have to, the client has to proactively keep programs. Unless that's why I was service.
Yeah, that's true. And if you're using a gateway aggregator, you could stop or you could do the retry management down on the service layer rather than up. But no, you know what? You're right though. Either way, the client still has to know that it has to stop retrying. So that's actually a good point. Yeah. I wonder if anyone's coded something that advanced where like you have a gateway or some kind of thing as a service, or that you can just sprinkle into an existing service with whether you're using these patterns or not, that also communicates up to the client and says, stop retrying now, we're broken, or something, right? I wonder if there's something that advanced yet. I don't think there is.
The service mesh is
The service mesh is trying to do that, yeah.
That sounds like something they're aiming for.
Yeah.
Well, we used to build that sort of a retry failure in the backend. So we're trying something to send back a message that, okay, failure. Someone will.
Right.
So,
Yeah.
the person can go and click the button again, but
At least the automated retry would stop.
he knows that he's not going to get an answer. Most likely, he's not saying he won't press the button.
Yeah.
You know, there's a retry after this came up from Azul.
Oh yeah.
Retry after. Yeah, then if the client recognizes it.
Well, okay. So are there any more questions from the internet? Okay.
Yes.
All right. Well, I think we'll wrap up this meetup for today. Thanks everyone for coming on this not so cold but definitely rainy Chicago day. Right.
Okay, sounds good.
I'm gonna stop sharing my screen now. Yeah. Thanks you all for coming.